Section 9.4 talks about vectors in 3 dimensions. So rectangular coordinates in 3 dimensions looks like this. You take the 2 dimensions, and what they do, they label the x-axis being there, the y-axis being there, and the z-axis being there. So if they switch on the axis, for example, the point 1, 2, you would move 1 to the right and 2 up. You're right there. If I want it 1, 2 in 3 dimensions, that would be the point 1, 2, 0. So you move 1 in the x, 2 in the positive y, and that point right there resembles this point right there. So if I wanted the point 1, 2, 3, you go 1 forward, so now you're along this line, 2 to the right, and you would move up 1, 2, 3, kind of like creating a rectangular prism. Just like here, you would create a rectangle to get to a point. That's why it's called the rectangular coordinates. Here, you're creating a rectangular prism just to get to a point. And if you want to label the point 2, you move 2 forward. Y is negative, so you don't move to the right, you move to the left 4 units. So that is 1, 2. You would move 1, 2, 3, 4, and you would go up just 1 unit. And that's where that point would be. And again, if you want to create the rectangle, you don't have to, of course. The floor looks like the traditional 2, negative 4, and then you're going to have to move up 1 unit. There it is. You could create that rectangle as well, and that point right there will be at the edge of that. The diagonal, of course, is running from the origin to that point. So our first example is to really plot a few of those, and let's start with some vectors in 3 dimensions. I would like to find the position vector AB in both forms. Alright, now you don't have to graph it. I am going to try and plot it just for practice. So this vector really starts at 2, 1, 1, and 3, 5, 4. The vector is right there. When we say find the position vector, we want to know if you start at the origin, where would you be? And vector AB would look like, again, end minus beginning, the same as what we did with the 2 dimensions. All the properties hold. 3 minus 2 is 1. 5 minus 1 is 4. And 4 minus 1 is 3. That vector is the same as you starting at the origin, moving 1 forward, 4 to the right, and 3 up. So those 2 vectors are identical. Again, I'm just plotting this for the practice. You really don't need to graph those. I suggest if you could start practicing some of those, you could see better. So again, here we have the initial point A at 3, negative 1, 3. You're right there. And it will be easier to see if you actually put the following units on it. Then you can see really how that works. And the second point, B, is at negative 2x. So we go backwards, 2 to the right. So 2, 2, and 5 up. 1, 2, 3, 4, 5. So this vector really looks like this. If I wanted to find this vector in standard form, by the way, I forgot to write, it says write it in both forms. You could also say AB equal I plus 4j, and the z direction takes k. Similarly here I could say, well, vector AB is actually end minus beginning, end minus beginning, and end minus beginning. If I move, that's a 2. So that vector right there, if you measure how many units you're moving forward, to the right and up, that's the same as you moving 5 back, 3 to the right, and 2 up. And that vector would look like this. It's kind of hard to see if somebody's looking at what I did. It's very hard for them to see what I did. But if you graph it, you could see it yourself and you could label it that way. That's not going to really matter here. We're just trying to find representation. Graphing is important, but you're not required to do that problem. Here, given a vector 1 forward, 3 to the right, 2 up, sketch the representation of the vector given the position. So pretty much given those points, if I am to start at 0, 0, 0, then this vector is simply moving 1 to the right, 1 forward, 3 to the right, and 2 up. You're right there. So the vector would look like this. You could figure out where it ends up being at by simply adding those. Now, if I take this point, if I am at the point 2, negative 1, 2. If I started right there, then this vector would move 1 in the positive x direction, 3 in the positive y direction, and 2 up. And that vector representation would be right there from that point. And if I take the third point, which is negative 4, negative 2, so I move to the left 2, and 3 down. And from that point I would move 1 forward, 3 to the right, remember this is under, and 2 up. And that vector would look like this. You could find what those coordinates are, but it's not asking for that. It's just saying find it. So we are finding it. And now if I go for the next, again, we're just repeating what we did with 2D to 3D. Given those vectors, find 3W. Well, W is right there. 3W will be negative 6I plus 3J plus 9K, or simply negative 6, 3, 9, using component form. W plus V would be, well, let's see, that is, you're going to add the components. You could write it out if you want. 1, 3, 2. I like component form. 1 minus 2, so just like we did with 2 dimensions, you add the I to the I, the J to the J, and the K to the K. And here 2W would be actually negative 4, 2, 6, minus 3 times V, 3, 9, and 6. 4 minus 3 is negative 7. 2 minus 9 is negative 7. Oh wow. And 6 minus 6 is 0. And there it is. Magnitude works the same way in 3D, same as 2D. If I want to find the magnitude of V, well, that is the square root. Normally we say the I component squared plus the J component squared. We'll just add the K and square it, and there it is. That is the square root of 1 plus 9 plus 4. The magnitude of vector V is the square root of 14. 3 times V, well, 3 times V, that's going to be the magnitude of 396. that would be the square root of 3 squared is 9 plus 81 plus 36. So if I'm not mistaken, that's the square root of 90. 90 plus 36, that is 126. You could simplify that if you wish. The magnitude of u plus v, well, you need to add those first. So that would be a 1 u plus v. U is actually negative 2, 1, 3, plus 1, 2, 3. Addition is commutative still in vector land, so that is a negative 1, a 3, and a 6. And the magnitude of this would be the square root of negative 1 squared plus 3 squared plus 6 squared, which is the square root of 10, 16. That would be a 4. Versus the magnitude of u. Well, the magnitude of u by itself is the square root of, and there's u. Negative 2 squared is a 4, 1 squared is a 1, and 3 squared is a 9. Plus magnitude of v, I already found it to be the square root of 14. So that would be the square root of 9, 10. Wow, did I make a mistake? They both have the same length? Oh yeah. It's just a coincidence. I didn't anticipate that, but it's all good. It doesn't matter. So again, do not mix those two. The magnitude of u plus v is not the magnitude of u plus the magnitude of v. That doesn't work that way. And if I go for the next problem, given this is v, given this is w, find a unit vector. If you remember, a unit vector in the direction of v, that would be v divided by its magnitude. I already found that. Well, what's the magnitude of v? We know that magnitude of v is actually the square root of 14. 1 squared plus 3 squared plus 2 squared. That's radical 14. So the unit vector, let's call it a, would be v divided by its magnitude. It would be 1 over radical 14, 3 over radical 14, and 2 over radical 14. Or you could simply say, if you wish, of course you could rationalize, and do not mix the points with the vector notation. How about magnitude of w? Well, if I want to find the magnitude of w, that would be the square root of negative 2 squared plus 1 squared plus 9. That's radical. Oh, that's working out the same way for both. That's not what we want. I made them. Okay, let me change that slightly. Let me just make that a 2. Just so that we're seeing something different. Otherwise, you might mix things up. So, negative 2 squared is a 4. 2 squared is a 4. 9. That is radical 17. So I could say vector a, which is a unit vector, that would be w divided by its magnitude. Any value divided by itself other than 0 has a length of 1. And there it is. So pretty much repeating what we did in 2D for 3D. And in this video, probably I could tackle a couple of more problems. Dot product works identical. That is, if I want to take u dot v, that would be 2 times 1 plus 2 times 1 plus 2 times 1. That would be 6. And if I want to find u dot v on b, that would be 3 times 2, which is 6, plus 1 times negative 6, plus 2 times 0, which is 0. And that tells us that those two vectors are perpendicular. We know that u is orthogonal to v. The same properties hold for 3D that held for 2D. Now, the same idea applies as far as vectors are perpendicular if the dot product is 0, and If one is a multiple of the other, they're parallel. Determine whether the vectors are parallel, perpendicular. If they're not parallel nor perpendicular, find the angle between them. We know here that V is 2 times, take that back, or half, I should say. I could do that. I could say V is half, right? Either I say V is half of U, or I could say that U is twice vector V. Therefore, they are parallel. And here, if I take U dot V, I know they're not multiple of each other. That would be 3 times 2, which is 6, minus 6, plus 0, which is 0. So we know that U is orthogonal to vector V. So, or I could say U and V are orthogonal. And if I come across a problem like this, in which one of them is not multiple of the other, if I take the dot product, U dot V, I will get a 1 minus 6 plus 4. So U dot V happen to be a negative 1. So I know that the cosine of theta equals U dot V. That formula still holds over the magnitude of U, the magnitude of V. So cosine of theta is negative 1 over the magnitude of U would be 1 plus 9 plus 4, that's radical 14. And magnitude of V would be 1 plus 4 plus 4, that's 9, that's 3. So I could say theta equal the inverse cosine of negative 1 over 3 radical 14. And if I plug this in my calculator, I could figure out what that angle is. I'm going to do that on my calculator and come back. And the angle turns out to be 95.1 degrees. And one more to go. Given a matrix takes on that notation. That's chapter 10, but I need this part for the next section, the cross product. So given a matrix, to find the determinant, so if you call this matrix A, the determinant is really the absolute value of A. Absolute value of A in matrix land. So in vectors, absolute value means magnitude. In vector land, if you take the absolute value of a vector, that's its determinant. That is a scalar. That's the cross of those. AD minus BC. So this is a scalar. Make sure that you get a number or a constant, however you want to see it. So if I look at the following vector, if I look at the following matrix, so A, the determinant of this, by putting an absolute value on it, you're saying find the determinant, or if you call it A, you put an absolute value on A. If it's a matrix, that means take 1 times 4, which is 4, minus 3 times 2, which is 6, that's a negative 2. Done deal. That's all you have to do. If I take the determinant of the next vector, the next matrix, by the way, a matrix is a list of vectors. It's an array of numbers, but they represent vectors. They have specific properties. If I want to find the determinant of this matrix, negative 3 times 1 minus 0 times 2, that would be negative 3. Now, if I have a 3 by 3, that's a bit trickier, and this is the part that I need for the next section. For the cross product, I need you to get this part. And this is something you're going to have to do. We're going to pick the first row. And for now, we're just going to memorize this. So we take the first entry, A, and we say it's going to be A times, and we cross A's row and column, 2, 4, 1, 2. So that would be A times, 2 times 2 is 4, minus, that would be 4. So this is 0A, or 0. always a minus when you pick the B. So if I cross B's row and column, I'm left with 1, 3, 4, 2. So that will be negative B times 2 minus 12. That's a negative 10. That is plus 10B. And when I get to the C part, plus C, and I cross C's row and column, I'm left with 1, 2, 3, 1. And that would be C times 1 minus 6, which is a negative 5 times C, which is negative 5C. And that would be my answer. You don't have to write this here, of course, but I'm leaving that in for your notes. Now, if I go for example D, and again, I need those more than I need. The only reason I did the 2 by 2, to do a 3 by 3, we need to reduce it. So if I go for the I, J, and K, well, that's what we're going to do. We're going to always take the first row. So if I take I cross I's row and column, what am I left with? I'm left with 3, 2, 5, negative 1. That is I times negative 3 minus 10. So that is negative 10I. Now, I will wipe out everything that I did, and I will go for the second entry. The second entry, we always put a minus J, always. And if I cross J's row and column, I'm left with 1, 2, 2, negative 1. That's negative J times negative 1 minus 4. That's a negative 5 times negative J, turns out to be plus 5J. And if I go back to the problem and I pick the last entry, which is K, I cross K's row and column, and I'm left with 1, 3, 2, 5. So that is K times 5 minus 6. That's a negative 1 minus K. And we need the analogy of part D for the cross product. And that's pretty much it for this section.